Okay, to continue our lesson on exponential decay, if you recall from the previous lessons when we talked about exponential growth, there was actually a model that we could use to represent the growth of something exponentially, and we had this model, and it was y equals to a times 1 plus r to the t power. Now, if we want to represent a similar model, but we want to deal with decay, so we're going to deal with the decay factor, we simply make a slight change in our model. And in this particular case, instead of 1 plus r, we're going to have 1 minus r. And this is going to tell us how much our model is going to decline by. So we have a decay factor. Now, a couple terms that you might need to know as you see problems. Sometimes you're going to see the word appreciation, and this is in reference to growth. So anytime we're dealing with a growth model, you're talking about the appreciation, and the appreciation is whenever the value of something grows. So maybe you buy a house and you sell it later on for more than what you bought it for. That house has appreciated. On the flip side of that, you can have something called depreciation. And we generally associate this with the exponential decay models. Depreciation is when something that you own loses value. So take, for example, a car. If you buy a car and you drive it for a couple years and you want to sell it, in the majority of cases, most cars lose value over that time period, and so the car has depreciated in value. So you really need to become familiar with appreciation in a value sense and depreciation in a value sense. So if we look at sample problem number 4, sample problem number 4 is actually a depreciation problem. So we're going to depreciate the value of a car. And in this case, we just simply use the term decreases, but sometimes people will use the word depreciation in place of decreases. So here we go. You buy a new car for $24,000. The value of the car decreases by 16% each year. So we have a depreciated value every year of 16%. What I want you to do is take your knowledge from the growth model and now take this decay model that we have given to you and apply it to sample problem 4. So in part A, you need to write a decay model. Keep in mind, when you're writing a model, we need to have 2 variables in our model, preferably the y in this case and the t, because the time is the one that can change. Then in part B, we give you a time factor for you to apply to the model. And then lastly, if you go down to the next page on part C, we ask you to give us a visual representation of the model that we can use to estimate potential values. So go ahead and use your experience from the previous lessons with the growth models and see if you can come up with A, B, C, and D's answers. Okay, so hopefully you pause the video and you're able to work those as best you can. I'm going to start here with part A, so we need a model to work with. So we're going to start our model using y equals a 1 minus r to the t power. So we have to come up with values of the a, the r. And so the a is our initial amount, so that's $24,000 as given in the problem. And then our rate is 16%. And keep in mind that we have to write that as a decimal for us to use. So we simply are going to move the decimal point back 2 places so that we can write this decay model. So I'm going to have y equals 24,000. Give myself some space here. Times 1 minus 0.16, and remember we needed 2 variables, so we have a y variable, and of course the variable that's unknown at this time is our time, our t value. Now to write this model correctly, what we need to do is we need to consolidate the parentheses. So we're going to say y equals to 24,000 times 0.84 to the t power. So this is the correct answer. Now, part B says asks us to estimate the value after 2 years. So now I can take that 2 years and I can apply it to the t value. So y equals 24,000 times 0.84 to the second power. And we would just simply use our calculator to come up with the answer for that. And that is going to give us $16,934.40. So what this is telling us is that if I bought this car at $24,000, brand new, after 2 years of driving it and probably taking care of it just fine, assuming it's gotten in no wrecks or anything, that it's going to decrease in value by 16% each year. So 2 years later, the amount that I could sell that car for would be roughly $16,900. Now, anytime you're selling a car or a house or anything in that matter, the price is really determined based off of what somebody else would actually pay for it. The 16% a lot of times is just a good guide as to what cars depreciate at. So every car has a different depreciation value based off of its quality. So let's take a look at the next parts of this. We're asked in Part C to graph the model. Well, in graphing the model, what we would need to do is we would need to create, as we always do, a t-chart. And in this case, we have time, and then we have the depreciated value, which is represented by y. And of course, we know that at year 0, when we first bought it, that car was still worth $24,000. And of course, in Part B, we said that 2 years after owning it, that car was worth roughly $16,934. Now, that's 2 really good points to start with, but we probably should go a little bit farther out just to know, just to give us a better view of the graph. And so, if you do 5 and you do 7, 5 years out, if you plug 5 in for t and punch it in your calculator, you're going to be left with a value of roughly $10,000. And then if you plug 7 in, it goes all the way down to $7,000 roughly. Now, we've been left a blank graph here, and we were only given quadrant 1, and that's because we can't have a negative value of years. So t represents years, and we can't go negative years. And then we hope that the value of the car never goes below 0, so you can't have a negative value for the car. It just becomes a hunk of metal at some point, and then you can just sell it off for scrap parts. But for this particular situation, the y-axis is the y, and that represents the value of the car. So we're going to create our own little scale here. And of course, you do this the best that you can, and try to make the little niche marks as similar as possible on both axes, so that it gives you a consistent look to your graph. And of course, since the value of the car it could be very high, we're going to have to come up with a scale that is easy to use. So I'm just going to do it in terms of $5,000 increments. 5,000, 10,000, 15, 20, 25, and then of course 30, and of course we never even had a value of 30 for our car to begin with. And then I would graph my t-chart points, and so here we go. 0, 24,000, and so remember these are represented in terms of thousands, so that's roughly 24,000. 2 and 16,000, of course we're just guesstimating this the best we can. 5 gives me roughly 10,000. And 7 gives me about $7,000, and you can see the general trend here. Now, since our graph is not really big enough to create, to actually get all the way down to the asymptote, we're just going to get the general trend in relation to what we already have on the graph and just draw that the best that we can. Okay, and so that's a graph of the model that we've created, and of course it's never going to look exactly right all the time because we're kind of freehanding a lot of the material. So if we look at T, it says to use the graph to estimate the value of the car at when the value of the car will be $12,000. So we can do this by simply finding roughly the $12,000 value. Now, if we do this, we can go over and we can see that our place on the curve for $12,000 is about right there where the red circle is. And if we want to know what year we'll have a $12,000 value in, we're going to say about, and of course this is an estimate, about year 3. So you can see it's going to take us about 3.5 years roughly, and our car will have depreciated to a $12,000 value. So that's just a little guesstimation based off of our graph that we are drawing. So this is just one small example of depreciation or a decay model. Please be familiar with this type of model and how to do all of these various parts.